Well, hi, this is Dr. James Wood for another class of Psych 1303 Statistical Methods. And the title of today's class is Type 1 Error, Type 2 Error, and Statistical Power. Now, before we begin today's lecture, uh, I'm going to review the main points from the last lecture. As we indicated in the last lecture, a researcher who does a two-group study always finds that the two sample means are different from each other. And the researcher then has to decide whether this difference is due to sampling error or instead whether it indicates a real difference between the underlying populations from which the samples are taken. The way to decide between these two options is to do a t-test. And a t-test has 5 steps. The first step is to conditionally assume that the null hypothesis is true and that the two population means are equal. Now, this is a conditional assumption. That is, when you're doing a t-test, you temporarily assume the null hypothesis is true so that you can test it out and decide whether it really is true. So that's the first step of a t-test. The second step is to calculate these 3 numbers. First, you calculate this number. This is the observed difference between the two sample means, and it's very easy to calculate. You have 2 samples from the 2-group study. You just subtract the mean of one sample from the mean of the other sample. Okay, now once you have that number, you go on to calculate this number, the expected value of the sampling distribution of the difference between two means. Now this number has a very long and scary name, but it's easy to calculate because if the null hypothesis is true, as you conditionally assumed earlier, then the expected value of the sampling distribution is 0. Now finally, you need to calculate the standard error of the sampling distribution of the difference between the two means. And there's a formula for this standard error, and you'll learn it in advanced statistics. But in this course, you don't need to know the formula. In this course, when you need the standard error of this sampling distribution, the book will tell you, or I will tell you, or your instructor will tell you what it is. So you don't have to worry about calculating that. So after calculating the 3 numbers in step 2, you're ready for step 3, which is to calculate the t-score for the observed difference between the means in the sampling distribution of the difference between the means. Now, in most circumstances, a t-score is pretty much the same as a z-score. When you see the word t-score, you should think this is just a variation on the z-score. When sample size is less than 30, the t-score and z-score may be different, but you don't have to worry about that. For everything we do in this class, you can assume that the t-score and the z-score are identical. So the observed difference between the means in our 2 samples is 2. The sampling distribution is normal, so we can write the z-score equivalence underneath the histogram. And we can see that an observed difference of 2 points between the 2 sample means is equivalent to a z-score of about 0.90. So this tells us that if 2 populations have the same mean, and if we draw 10,000 paired samples from these 2 populations and calculate the difference between the 2 means, we will get a difference of 2 fairly often. Now, just by looking at the sampling distribution, we have estimated that t is approximately equal to 90, or excuse me, to 0.90. But usually we need to calculate the exact t-score, and that is fairly easy. Here's the formula for t. It looks complicated, but is really very simple. It only has 3 parts, and we already calculated each of these 3 parts in step 2. The first part up here is the difference between the two sample means. The second part is the expected value of the sampling distribution of the difference between the means. And the third part is the standard error of the sampling distribution. Now, as you recall, because we began by assuming that the null hypothesis is true, the expected value of the sampling distribution is 0. So the formula for the t-score simplifies to this. And this formula is really very simple. The t-score is the observed difference between the means divided by the standard error of the sampling distribution. Now, there's an underlying logic to this t-score because the t-score is really a z-score, at least most of the time. When you calculate a z-score, you start with the raw score of an individual, you subtract the mean, and then you divide by the standard deviation. When you calculate the t-score, you start with the difference between two means, and then you subtract the mean. In this case, the mean is called the expected value, and then you divide by the standard deviation, which in this case is called the standard error. So once we have t, we're ready to go on to step 4. We ask, is t in the critical region? Critical region is the 5% of least likely t-scores. This histogram shows the same thing, that the critical region consists of the 5% of least likely t-scores. If the answer is yes, t is in the critical region, then we say that p is less than 0.05. But if the answer is no, t is not in the critical region, then we say that p is greater than 5, or greater than 0.05. Now, p is an abbreviation for probability. The probability of obtaining a t-score this large or larger if the null hypothesis is true. Now, let me put it another way. If the difference between the population means is truly 0, then the probability that the sample means will differ this much from each other is 5% or less. Okay, now we're ready for the 5th and final step of the t-test. If p is greater than 0.05, we conclude that the observed difference between the means is not statistically significant, and we accept the null hypothesis. In other words, we conclude it looks like the population means may be the same. Now, on the other hand, if p is less than 0.05, we conclude that the observed difference between the means is statistically significant, and we reject the null hypothesis. That is, we reject the idea that the population means are the same. This means that the observed difference between the sample means is very large and very unlikely to be due to sampling error. Instead, the two population means really are different from each other. Instead of the Null hypothesis, we accept the alternative hypothesis. The alternative hypothesis states that the population means are different. So that covers the t-test, at least so far. And now we're ready for today's new topics. First, today, we're going to focus on type 1 and type 2 error. Now, these errors can occur whenever we do a t-test or any other kind of null hypothesis significance testing. Now, let's start with type 1 error. A type 1 error occurs when, in fact, the population means are the same, but the t-test indicates that the difference between the sample means is statistically significant. Now, to see why type 1 error occurs, let's consider the sampling distribution of the difference between two means when the null hypothesis is true. That is, the means of the underlying populations are the same. Because the null hypothesis is true, the sampling distribution of the difference between the means has an expected value of 0. Now, if I randomly select paired samples from this distribution, find the difference between the sample means, and calculate the t-score, or excuse me, not when I do, but if I do that, if I randomly sample them and calculate the t-score, this t-score will lie in the critical region exactly 5% of the time. If the t-score lies in the critical region, I'll conclude that there's a statistically significant difference between the means, and then I will wrongly conclude that the underlying population means are different. But that's an error. Now let me repeat, this is a sampling distribution where there's no difference between the population means. But for 5% of these samples, or pairs of samples, the t-test wrongly indicates that there is a difference between the population means. The t-test is wrong 5% of the time. Now this is as good as any time to mention the two red lines that are the boundary between the critical region and the rest of the sampling distribution. These lines mark the critical values. The critical values are the values of the t-scores at the edge of the critical regions. We can see that the critical values for this distribution are 2 and -2. In other words, if t is greater than 2, it lies in the part of the critical region on the right. And if t is less than -2, it lies in the part of the critical region on the left. Okay, now we know what the critical value is and how it marks the boundary or edges of the critical regions. Let's get back to type 1 error. The symbol for the probability of type 1 error is the Greek letter alpha, which looks a lot like an A. Alpha is equal to the area of the critical region. So the probability of making a type 1 error is the same as the area of the critical region. When researchers do a t-test, they normally use an alpha of 0.05. So the critical region for the t-test includes the 5% of least likely t-scores. And the probability of making a type 1 error is also 5%. Now, when you think about it, this is a little shocking. When you read in a journal article, we found a significant difference between the means, and so the underlying populations are different, the article is wrong 5% of the time. Yikes. Now, we don't need to lose faith in researchers because their t-tests are wrong 5% of the time. Type 1 error is unavoidable. It's not due to any mistake or sloppiness by the researcher. It's just a feature of the t-test and of null hypothesis significance testing in general. When the t-test is used and the results are statistically significant, it's unavoidable that there is a 5% probability of type 1 error. Now, type 1 error can be reduced. The researcher can decide, I do not want to have a 5% chance of type 1 error. I'm too good for that. So I'm not going to use an alpha of 0.05. Instead, I'm going to use an alpha of 0.01. So that way, the probability of my making a type 1 error is only 1%. Now, remember that alpha represents two things. First, it's the probability of making a type 1 error. And second, it is the area of the critical region. So when the researcher chooses alpha equals 0.01, the size of the critical region also changes. So here in this slide, you can see the same sampling distribution you saw earlier. The red bars, which represent the critical values, are in the right position for alpha equals 0.05. In other words, the area of the histogram outside of these bars, outside the critical values, is 5%. Now, I want you to watch what happens to these bars when alpha is changed from 0.05 to 0.0. Watch the bars. This is an alpha of 0.05, and this is an alpha of 0.01. Now I'm going to do it again. Watch what happens to the bars, the critical values. This is alpha equals 0.05, and this is alpha equals 0.01. I'm going to do it one last time. Alpha 0.05, alpha 0.01. So can you say, if I were here in person with you, I'd ask you, what happens to the bars when I go from alpha equals 0.05 to alpha 0.01? How would you describe that? Okay, kind of formulated an answer? Well, you could say that the bars, the critical values, move apart when we go from 0.05 to 0.01. So this is alpha equals 0.05 again. And in a moment, I'm going to show you alpha equals 0.01 again. But this time, I want you to watch what happens to the area of the critical region. That's the area of the histogram that's outside the red bars, that's outside the critical values. Ready? This is alpha 0.05. This is alpha equals 0.01. One more time, alpha 0.05. Watch that critical, watch the size of the critical region. This is alpha 0.01. One last time, watch the areas. This alpha 0.05, alpha 0.01. So you see what happens to the critical region when I go from 0.05 to 0.01. The critical region gets smaller, a lot smaller. When alpha is 0.05, the area of the critical region is also 0.05. When alpha is 0.01, the area of the critical region is 0.01. So it's only about 1/5 as big. I'll show you one more time. Alpha equals 0.05. Alpha equals 0.01. So that's the good part of setting alpha equal to 0.01. It reduces type 1 error. There's a bad part though. It increases another kind of error. And that is type 2 error. Type 2 error occurs when in fact the population means are different, but the t-test indicates that the difference between the sample means is not statistically significant. Now, to illustrate type 2 error, we'll consider a two-group study in which there really is a difference between the two underlying populations. The mean of the first population is 6 points higher than the mean of the second population. Now, a researcher has drawn a sample from each population and calculated the sample means. The difference between these sample means is 3 points. So in the population, the means are 6 points apart, but in the samples, because of sampling error, they're 3 points apart. So the population means really are different, but when the researcher does a t-test, the t-test indicates that the sample means are not significantly different. And this is an example of type 2 error. There really is a difference between the populations, but the t-test says there is not a significant difference between the two sample means. Now, to see how this can be, let's look at two sampling distributions. These are two sampling distributions for the difference between two means. The sampling distribution on the mean is the true sampling distribution. The true difference between the two underlying population means in our example is 6. And as you can see, the mean of this sampling distribution is also 6, right? Because it's the sampling distribution of the difference between the two means. So when the population means differ by 6, the mean of this sampling distribution is also 6. Now on the left is the sampling distribution of the difference between two means when the null hypothesis is true. Now we have been using this sampling distribution a lot so far. What is the mean of this sampling distribution on the left? Ask yourself that. Okay, now this is the mean. This is the sampling distribution when they're on the left, when there's no difference between the population means, and its mean is 0. We've talked about that, when it's the sampling distribution of the difference between two means, when the null hypothesis is true, then the expected value is 0. Now, when a researcher does a t-test, she conditionally assumes that this distribution on the left is the true distribution. She doesn't realize that, in fact, the true sampling distribution is the one on the left. Excuse me, she doesn't realize that, in fact, the true sampling distribution is the one on the right. The one on the right is the true one. The one on the left is the one that the researcher conditionally assumes. Now, when the researcher does the t-test, she uses an alpha of 0.05. So the area of the critical region is 0.05. And in this graph, it's marked in red in the tails. The critical values are indicated by black bars. Now, in our example, the observed difference between the sample means is 3. And this graph shows the difference between the sample means in our example. The gold dot on the x-axis indicates that in our study, the difference between the two sample means is 3. Now, here's a question to ask yourself for a minute. I'm going to give you a moment to think about it. When the researcher does the t-test, will t lie in the critical region? Okay, so to repeat the question, when the researcher does the t-test, will t lie in the critical region? The answer is no. Red areas are the critical region. The gold dot represents the observed difference between the two sample means. Now, the dot doesn't lie within the red areas, so T does not fall within the critical region. Now, here's another question. Will the researcher conclude that the observed difference between the sample means is statistically significant? Now, let me repeat that. The researcher found that the observed differences between the means is 3, and 3 does not lie in the critical region for the distribution on the left. So which is the sampling distribution of the difference between two means when the null hypothesis is true. That is, when the population means are the same. Now, if the researcher gets this difference between the sample means of 3, will the researcher conclude that the observed difference between the sample means is statistically significant? Okay, ready? Okay, so the answer is no. If T doesn't fall in the critical region, then the researcher accepts the null hypothesis and concludes that the difference between the means is not statistically significant. In other words, the researcher commits a type 2 error. Now, we know that in fact, the difference between the population means is not equal to 0. It's equal to 6. But the researcher has no way of knowing that and makes an erroneous decision. Now, notice that in the middle of the graph, a green area has been filled in. This green area is the left end of the true sampling distribution. The green area represents paired samples from the true sampling distribution, whose means do not differ very much from each other. The gold dot represents one of these paired samples. In this paired sample, the difference between the sample means is 3 points. Now, here's another paired sample where the difference between the sample means is only 1. Now, the paired samples that produce point came from the true sampling distribution on the right. However, the difference between the sample means in this paired sample happens to be very small due to sampling error. And so this difference of 1 lies to the left of the critical value. Now, if the researcher happens to draw this particular paired sample, or any paired sample from the green region, the t-score will not lie in the critical region. And the t-score will not be statistically significant. The researcher will then wrongly conclude that the population means are the same. In other words, the researcher will make a type 2 error. Remember, the green area represents all the paired samples where the researcher will make a type 2 error. Now, how often will the researcher make a type 2 error? Well, the area of the green region in this example is 0.16. That is, 16% of the samples in the true distribution fall into the green region. So for 16% of the paired samples, the researcher will make a type 2 error. Put another way, the probability of making a type 2 error is 16%. Now, the symbol for the probability of type 2 error is the Greek letter beta, which looks a lot like a B. So in this example, beta equals 0.16. So the probability of type 2 error is beta. And geometrically, beta is equal to the area of the true sampling distribution that is less than the critical value. Now, type 2 error, like type 1 error, is unavoidable. It Type 2 error is not due to a mistake by the researcher. There will always be some risk of type 2 error anytime we use the t-test or any other type of null hypothesis significance testing. Now, now I'm going to tell you something that's a little unpleasant to think about, particularly for researchers. It's shocking to say, but reducing type 1 error increases type 2 error. Now, earlier I said that a researcher who wants to reduce the probability of type 1 error might decide to use an alpha of 0.01 instead of an alpha of 0.05. Using an alpha of 0.01 does in fact reduce the probability of type 1 error to 1%. But here's the bad news, it also increases the probability of type 2 error. I'll show you by presenting a comparison of what happens when a researcher is using alpha of 0.05 and what happens when she decides to use an alpha of 0.01 instead. Now, these are the two distributions we were looking at earlier. The distribution on the right is the true distribution, where the difference between the population means is 6. The distribution on the left is the sampling distribution when the null hypothesis is true. Now, let's imagine a researcher draws paired samples, computes t, and sees if t lies in the critical region of the sampling distribution with alpha equals 0.05. Now, ask yourself, what color is the critical region in this slide? That's right. In these slides, the critical region, which has two parts, is red. And what is the area of the critical region? Remember? Well, it said alpha is 0.05. That's up at the top of the slide. So alpha is also the area of the critical region. So the red areas are 5% of the distribution on the left. And here's another question for, what is the probability the researcher will make a type 1 error? Okay, the answer to that one is the probability of making a type 1 error is the same as the area of the critical region, which we just said is 5% or 0.05. Now, I want you to keep your eye on the critical region, which is red. Watch what happens if the researcher decides to set alpha to 0.01. Aha! We saw this earlier. I'll do it one more time. Watch the red region. Alpha equals 0.05, alpha equals 0.01. So what happens to the critical region when alpha is 0.01 instead of 0.05? Aha, you remember that from earlier, right? The critical region gets smaller. And what happens to the probability of making a type 1 error? What happens to the probability? Well, it gets smaller too, right? Now let's focus on the critical value. In this slide, ask yourself, how is the critical value represented? Well, there are actually two critical values, one on the left and one on the right. Both of them should be represented by black lines, but I notice the one on the left is missing. But on the right, you can see the black line that marks the boundary of the critical region on the left. Now, I'd like you to watch what happens to the critical value, that is the black line on the right, when the researcher switches from alpha equals 0.05 to alpha equals 0.01. Here's alpha equals 0.05. Here's alpha 0.01. I'll do it one more time. Watch the line that represents the critical value. Alpha equals 0.05. Alpha equals 0.01. So what happens to the critical value on the right when the researcher switches from alpha 0.05 to alpha 0.01? Well, you're right. It moves to the right, doesn't it? Yes. Now, I want you to focus on the green area of the graph that represents type 1 error. Remember, geometrically, beta is the area of the green part of the graph. So in this slide, alpha is 0.05 and beta is 0.16. Now watch what happens to the green area, beta, when the researcher sets alpha to 0.01. Aha! Do you see what happens to the area of the green when alpha is set at 0.01? That's right, it gets bigger. Now what is beta when alpha is set at 0.01? It's right there in the graph. What is beta equal to when the researcher sets alpha at 0.01? Okay, I'll do it one more time just to make sure you saw it. Watch the green area that represents beta. Alpha equals 0.05. Alpha equals 0.01. So here's the moral. By setting alpha at 0.01, the researcher reduces type 1 error, the red part. But setting alpha at 0.01 causes type 2 error, that is the green part, to increase. As this slide shows, if the researcher sets alpha at 0.01, then beta becomes 0.34. This means that about 1/3 of the time, the researcher will make a type 2 error. Remember, because beta is equal to the probability of making a type 2 error. So that is, even though the population means are really different, the researcher will wrongly conclude that the population means are the same and the null hypothesis is true about 0.34 of the time. That's about 1/3 of the time. So the sad truth is that when we reduce alpha, the probability of type 1 error, we always increase beta, the probability of type 2 error. It seems like a no-win situation. But I'm happy to say there is a way to keep both alpha and beta small. And I'm going to tell you about that in a few minutes. But before we do that, I need to discuss something else. The technical definitions of type 1 and type 2 error. Now, so far in this lecture, I've used definitions of type 1 and type 2 error that are accurate, but they're not the technical definitions. The technical definitions are the ones you'll find in rigorous statistics books. You'll need to know these definitions so that you can recognize them when you take advanced statistics courses. So here's the technical definition of type 1 error. Type 1 error is rejecting the null hypothesis when in fact it is true. Now, sometimes you might find this definition easier to understand if you look at the bottom part first and then the top part. So at the bottom part, if the null hypothesis is in fact true, which means the population means are the same, then move up to the top part, then it's a type 1 error to reject the null hypothesis and conclude that the population means are different. Okay, now here's the technical definition of type 2 error. Type 2 error is accepting the null hypothesis when in fact it's false. Now again, you might find it easier to look at the bottom part first. If the null hypothesis is in fact false, that means the population means are different. And then to the top, so it's a type 1 error to accept the null hypothesis and conclude that the population means are the same. Now these definitions are kind of hard to think about. Everybody has trouble keeping these two technical definitions straight and remembering them. For instance, if you want to embarrass one of your professors, ask them for the definition of type 1 error, or better yet, ask them for the definition of type 2 error. There's about a 50% chance your professor will have to stop and think hard and then will still give a wrong answer. So it is hard, but I'm going to give you some hints that may help you to keep these two definitions straight. One hint is don't rely on memorization. Memorization doesn't work in the long run to try to remember the difference for type 1 and type 2 error. You may memorize the definitions for the final exam in this course, but then when you take advanced statistics next semester, you'll find that you're kind of hazy about these definitions. Your professors, I have to tell you, your professors once memorized these definitions and then their memories got hazy too. So this is a losing proposition to rely on memorization. But instead of relying on memorization, you can use two mnemonics that will help you to remember the definitions. Now, mnemonics is a word that means memory tricks. They're gimmicks to help you remember. Now, a very effective mnemonic trick is to create images that will help you remember. And research shows that these images, you're more likely to remember them if they're ridiculous or violent or obscene. The more ridiculous or violent or obscene the image is, the more it will help you remember. Now, in this class, I am not going to teach you violent and obscene images. Instead, I'm going to use ridiculous images. So here's the definition of type 1 error again. And I want you to notice it's about the null hypothesis. Now, here's the technical definition of type 2 error. And I want you to notice that it also is about the null hypothesis. So the first thing you need to remember is that it's all about the null hypothesis. Type 1 and type 2 error are all about the null hypothesis. The alternative hypothesis, remember that? Well, it isn't even mentioned in the technical definition. Only the null hypothesis is. Now, next, here's a mnemonic that might help you to remember this. It's a cartoon with the null hypothesis talking. Now, you may say this cartoon is dumb and ridiculous, and I agree. But because it's dumb and ridiculous, it just might help you remember that type 1 and type 2 error are all about the null hypothesis. Now, the second thing you want to remember is that type 1 error involves rejecting the null hypothesis. Right? Type 1 is about rejecting the null hypothesis. Type 2 is about accepting the null hypothesis. So here's another dumb cartoon to help you remember that type 1 error is the one that's about rejecting the null hypothesis. Okay, so the null hypothesis is narcissistic and thinks he's number 1. You get it. Well, maybe this mnemonic is just too dumb to work. But more likely, it's so dumb it will work. And some people have found it helpful. Now let me show you how it can help. Suppose you have to remember what type 1 error is. You just remember the cartoon with the narcissistic null hypothesis saying, I'm number 1, and it's an error to reject me. This should be enough to remind you that type 1 error is rejecting the null hypothesis. Okay, I'm number 1. It's an error to reject me. And if it's an error to reject the null hypothesis must be true. For type 2 error, you just remember that type 1 error is rejecting the null hypothesis, and that it must be then that type 2 error is about accepting the null hypothesis, because remember, it's all about the null hypothesis. And if type 2 error is about accepting the null hypothesis and that's an error, then the null hypothesis must be false, right? If it's an error to accept the null hypothesis, then the null hypothesis must be false. Now, like I said, the mnemonic I showed you, or in the two cartoons, they help some people. And I'd be interested in knowing whether it helps you, particularly whether it helps you remember in the future, long after you finish this class. So next year, when you take advanced stats, or when you're a professor yourself, you can write me and say, you know, that mnemonic was great. It really helped me remember the difference between the type 1 error and type 2 error. Or you can write me and say, you know, that cartoon, it was absolutely helpless. My students asked me today in class, what is type 2 error? And I couldn't say. So you can write and let me know in the future. Or better yet, maybe you'll come up with a better mnemonic yourself. If you do, send it to me as a cartoon and maybe I'll put it in this class in the future. Now, if you like this idea of using mnemonics and images to improve your memory, I recommend the memory book by Harry Lorraine and Jerry Lucas. You can get a used hardback copy on Amazon.com for 1 penny plus $3.99 shipping. Now, $4, it's a great bargain. I've used it throughout my adult life, and it helps me to memorize lists for my class, or it can even help you, if you have something tough you have to memorize with 8 parts, this book will help you to remember it. Believe me, it's really helpful. Okay, so now let's go on to a new topic today, statistical power. Now that you understand what type 1 error is and type 2 error and how they have a no-win relationship, and if we try to decrease type 1 error, we end up increasing type 2 error. We understand that. Now we're ready to learn about statistical power. Now, the phrase statistical power has an electric charge. For example, statistical power means that statistics are powerful and that people increase their power by learning statistics. And of course, this is true. Statistical power is also what you have gained by your hard work in this course. By now, you're masters of correlation, wizards of regression, superheroes of the standard error. You are statistically powerful. And I'm going to give you a little demonstration of your powers that you've learned, why you can even sometimes read minds when it comes to numbers, thanks to taking this course. Now, I'm going to give you an example. First of all, I want you now to pick any number between 1 and 100. So go ahead, pick any number between 1 and 100. Okay, now it so happens that I am thinking of the date that my first grandchild was born. And I think that the number you have chosen through intuition and your statistical power will help you to guess what year my first grandchild was born. Okay, still got that number? Okay, let's take it and add the 2 digits together. So like if you chose 75, add the 2 digits together and you get 12. Okay, now if you get 12, that still has 2 digits. You want to get to 1, so add 1 and 2 and you get 3. Okay, so do that. Keep adding together the digits of the number you selected until you're down to a single digit. Got it? Okay. Now, I now have 5 grandchildren, so I want you to multiply that number that you just calculated with 1 digit. I want you to multiply that number by 5. You got it? Okay. Now, 2 of the grandchildren are girls, so I want you to multiply it again by 2. Okay? So you multiply by 5, you multiply by 2. That's great. And finally, 2 of my grandchildren live out of town, so subtract 2 from the number you just got. Okay, now you should have a number. And if the number has 2 digits, throw away the lower one. So if you chose like 35, throw away the 3. Okay? Now you should have 1 digit left, right? And that Now I'm going to tell you the date. Remember that digit. The date that my first grandchild was born was 2008. If you chose the number 8, you can give yourself credit for having statistical power. But I have to say that statisticians, when they talk about statistical power, usually mean something less magical than this. Because for a statistician, power is equal to 1 minus beta. Now, as you remember, beta is the probability of committing a type 2 error in a t-test or other form of null hypothesis significance testing. So statistical power is the probability of avoiding type 2 error. Now this is a graph you've seen several times before. On the left is the sampling distribution of the difference between the sample means when the null hypothesis is true, and it's mean 0. On the right is the true sampling distribution. The difference between the two population means is in fact 0, and so the expected value, the mean of this sampling distribution is 6. Now, when we draw paired samples from the two populations, and on the right, which is the true population on the right, and compute the difference between the sample means, this is the sampling distribution that we get, the one on the right. Now, the green area shows beta, the probability of making a type 1 error. So if you perform a t-test, it's the probability of making a type 2 error if you perform a t-test. And the green area is the part of the true sampling distribution that's to the left of the critical value for the t-test. Now, the yellow area is new. The yellow area is simply the part of the true sampling distribution that's not in the green area. Its area is 1 minus beta. Remember, because all density distributions, their area is 1. So because beta is 16, the yellow area must be 0.84. Now this yellow area represents statistical power, and we can think of it in two ways. First, the yellow area is simply equal to 1 minus beta. Second, the yellow area represents those paired samples whose means differ a lot, so that the t-score for the difference is larger than the critical value. These are the paired samples that will be statistically significant when the researcher performs the t-test. So let me repeat. The distribution on the right represents the differences between means for many, many paired samples. The green region indicates the paired samples that have a small difference between the means. When a t-test is performed for paired samples in the green region, the difference between the sample means is not going to be statistically significant. And the area of this green sector is equal to beta. The yellow sector indicates the paired samples that have a relatively large difference between the means. When a t-test is performed, the difference between the sample means is statistically significant. The area of the yellow sector is 1 minus beta, and that's the statistical power. And you can see beta plus power equals 1. 1 minus beta equals 0.84, and also 1 minus power equals beta. So let's see what happens to statistical power if we change alpha. In this slide, alpha is 0.05 represented by the red regions. Watch what happens to the yellow region when alpha is changed to 0.01. Aha! When we switch from an alpha of 0.05 to an alpha of 0.01, the yellow area gets smaller. That is, when we use an alpha of 0.01, power decreases. Now, earlier in the lecture, we learned that switching to an alpha of 0.01 increases beta, the probability of type 2 error. type 2 error. So if beta increases, that's the green part, then power automatically decreases, that's the yellow part. So switching to alpha equals 0.01 decreases power. Now, here's another way of thinking about statistical power. Power is the probability of finding a statistically significant difference between the sample means when the population means really are different. The true sampling distribution is on the right. The yellow region represents the paired samples with a big difference between the sample means. And for these paired samples, the difference between the sample means lies to the right of the critical value and is statistically significant. Now, the area of this yellow region is equal to power. In this example, power is 0.84. So the probability of finding a statistically significant difference between the means is 0.84 or 84%. Now, earlier today, we learned that setting alpha to 0.01 instead of 0.05 has the good effect that it reduces type 1 error. But it has a sad side effect. It increases type 2 error. And because setting alpha equal to 0.01 increases type 2 error, it automatically decreases power. Because increasing type 2 error always decreases power. Now, this is a very sad and tragic situation. What we'd like is to simultaneously reduce type 1 error and keep type 2 error small and increase power, right? We want to do all those at the same time. Now, a few minutes ago, I said there's a way to keep both type 1 and type 2 errors small and get lots of power. As it happens, there's a fairly easy way to do this. You do it by increasing the size of the samples in the study. That is, the researcher needs to collect samples with more people in them. Now, increasing sample size has several good effects. First, it keeps alpha low at 0.05 or 0.01. In other words, when you increase sample size, you can just keep alpha as low as you want it. The probability of type 1 error stays low. Second, increasing sample size decreases beta. In other words, the probability of type 2 error is also low, just like alpha is. And third, increasing sample size increases power. In other words, the chances that we'll find a statistically significant difference goes up. Now let me show you why increasing sample size has these wonderful effects. Let's suppose the size of our samples is 100. The sampling distributions look like this, right? On the left, sampling distribution when null hypothesis is true. On the right, sampling distribution when it is really true, which is the truth, that in the populations, the sample means really do differ by 6. Now, in this example, the red regions are very, very small because alpha is 0.01. But the green region is very large, indicating beta is 0.34, and power, the yellow region, is 0.66. But I want to show you what happens when we increase the sample size to 200. The red region representing, now this is with sample sizes of 200. The red region representing alpha of 0.01 remains very small. It stays the same size. But the green region, representing the probability of type 2 error, is much smaller. Beta is only 0.04, not 0.34. And look at the yellow region, which represents power. Oh, goody, power is 0.96. And now I'll show you what happens when we increase the sample size to 400. Now remember, the difference between the population means is still 6. Here, the red region you can see representing alpha stays the same. It's still very small. The probability of type 1 error is still 0.01, but the green region has shrunk so much that it's practically invisible. Beta, the probability of type 2 error is less than 0.001, and the yellow area representing power has grown. Power is now 0.999, which is practically equal to 1. Now, I'm going to show you the 3 slides again so you can see what's happening. First, I want you to see how increasing sample size makes the 2 sampling distributions narrower. So look at the width of the 2 sampling distributions, the width of these 2 sampling distributions. Now, here are the 2 sampling distributions when sample size is 100. Watch what happens to their width when sample size increases. Here are the sampling distributions when n equals 200, and here they are when sample size is 400. So you see what happens to the width of the sampling distributions when sample size increases. When sample size increases, the sampling distributions get lower. Their standard error gets smaller. And remember, what you're doing is you're dividing the standard deviation of the population by a larger and larger n. So the standard error gets smaller, the width of the distributions gets smaller. Now let's see what happens to alpha, the probability of type 2 error. Watch the red region. Here's a sample size of 100, 200, 400. So what happens to alpha? The probability of type 1 error as sample size increases? That's right. Alpha stays the same, which is good. We started out small, it stays small. Now let's watch what happens to the green region, which is type 2 error. Here's a sample size of 100. Watch that green area, that's beta. Here's a sample size of 200. And here's a sample size of 400. So what happens to beta, the probability of type 2 error as sample size increases? That's right. As sample size increases, beta, the probability of type 2 error gets smaller and smaller. And finally, I want you to look at what happens to the yellow area, which represents statistical power. Here's a sample size of 100. Watch that yellow area. Here's a sample size of 200. Here's a sample size of 400. What happens to statistical power as sample size increases? That's right. As we increase sample size, power increases. Increasing your sample size increases the probability that the t-test will be significant, assuming that the sample means really are different. So, what's the moral? Increasing sample size decreases the standard error of the sampling distributions. When the standard error is smaller, the sampling distributions are narrower and there's less overlap between them. This decreases beta, the probability of type 2 error, without changing alpha, the probability of type 1 error. And decreasing beta increases power. So increasing sample size keeps the probability of type 1 error constant while decreasing the probability of type 2 error and increasing power. And that's a great situation to be in. The bottom line is that there are big advantages to using the large samples. You can keep type 1 error small while also making type 2 error small. Now, before we finish, let's sum up the main lessons today. We learned about type 1 and type 2 error. If we make a type 1 error if we say, I found a significant difference between the sample means, when in fact the population means are the same. The probability of making a type 1 error is called alpha, and in most research, alpha is 0.05. Now, with type 2 error, that occurs when we say there's not a significant difference between the sample means, boo-hoo, but in fact, the population means are different. It's really great. The population means were different, we missed it. The probability of making a type 2 error is called beta. Now, we also learned that type 1 and type 2 error have a very sad relationship. If we try to increase type 1 error, we end up increasing type 2 error. However, there is a way to get low type 1 error and low type 2 error at the same time we increase our sample size. And finally, today we talked about statistical power. In a t-test, statistical power is the probability that we will find a significant difference between the means if there really is a difference in the population. Put another way, power is the probability of correctly detecting a difference in the populations when there really is a difference in the populations. Power is equal to 1 minus beta, and 1 by beta. Now, there's one more thing I should mention before I end, is that I don't have any grandchildren, and as far as you guessing the year 2008, well, let's just say that that was just a little sneaky. But I hope you enjoyed it. I hope it lightened up statistics for you today, and we'll see you again in the future. Goodbye.